Gravity, right. I mean, it's like it's everywhere, always there. But then you read an article like this one, and you start to realize how much we actually don't know about it.
Yeah, it's one of those things like you think you've got a handle on it,
And
and
you think,
then,
like, boom.
yeah,
Well, it's like, wait a minute. This
exactly.
article, it's suggesting that Einstein, he might have only gotten us halfway there
It's true. A lot of physicists have been wondering about that.
about this whole curved space-time thing. Like, what if that's not the whole story?
And that maybe gravity, it's like more than that.
Yeah. Like maybe it's a force, kind of like how electromagnetism works.
Exactly. A force in its own right.
Okay, so before we get too far into it, gotta ask, for those of us who, didn't spend years in a physics lab,
Sure.
this whole idea that Einstein's picture of gravity with like the equivalence principle and all that,
Yeah.
it works great for explaining how planets move and galaxies do their thing.
Right. It's been incredibly successful in that sense.
But could it be like a secondary effect, a consequence of something even more fundamental going on?
That's what's so fascinating about this article. It's exploring that possibility that those principles we take for granted, they might be results, not the cause.
Okay, so walk me through that a little bit. What's this article proposing?
Well, basically, it suggests that if you try to make a theory of gravity that's, mathematically self-consistent, and by that we mean the math doesn't contradict itself, everything adds up, then what emerges naturally is gravity behaving like a force.
Hold on. Mathematically self-consistent? That sounds kind of complicated. Like, what does that even mean in, like, plain English?
It just means the math has to make sense, no loose ends. It's like the universe has rules, and those rules have got to work together, right?
Okay, so it's like making sure the math of gravity plays nicely with the math we use to describe the tiniest particles, like in quantum mechanics. And when you do that,
Gravity acting like a force just kind of falls out of the equation.
whoa, okay, that's pretty wild.
And you know what's really cool? This approach, it could totally change how we think about one of the most basic parts of Einstein's work, symmetry.
Symmetry. Now, you're going to have to explain that one because when I hear symmetry, I think, like, a butterfly's wings. How does that fit into all this gravity stuff?
Well, in physics, symmetry means that the laws of physics are the same everywhere and for everyone. No matter where you are in the universe or how you're moving, those laws don't change.
So Einstein was all about this symmetry thing.
Oh, absolutely. He built it into his theories. It was hugely important for his work.
There's a buck coming. I can feel it.
But this article, it asks a really interesting question. What if this symmetry, instead of being this, fundamental rule that's just hardwired into the universe,
What if it's not?
what if it's more like a natural result of the way gravity works at a deeper level?
Whoa. So we're saying Einstein built this idea of symmetry into his theories, but like it might not actually be a starting point, more like a result of something even more fundamental.
Yeah, it's like to make gravity work the way it does, the universe kind of has to have this symmetry thing going on.
Okay, I think I'm starting to get with you on that, but where does this all lead? Like, what's the next step in this whole gravity puzzle?
Well, here's where it gets really interesting, you see. Thinking about gravity as a force, like we've been doing, it actually lines up with some really cool stuff we've been seeing in physics lately.
Really? Like what?
Well, for example, remember a few years back when they detected those gravitational waves?
Oh, yeah. Those ripples in space-time, right? From
Yeah.
those black holes colliding.
Exactly. That was huge, because it showed us,
It was like the biggest science news for months. Everyone was talking about it.
yeah, and it was big for a reason because it showed us that gravity, it can actually carry energy and information across like huge distances, just like electromagnetism.
Okay, I'm seeing where you're going with this.
Right. It's like the universe sending signals, but instead of using light or radio waves, it's using gravity.
Whoa, that's wild. And if gravity can do that, does that mean it might have its own, like, force-carrying particle?
That's the million-dollar question.
Yeah.
You see, in physics, there's this pattern, right? Like forces are usually carried by specific particles.
Right, like light has photons.
Exactly. So for gravity, we have this idea of a graviton, which would be the particle responsible for carrying the force of gravity.
So have we found this graviton yet?
Not yet. It's still hypothetical for now.
Okay, so it's like the missing piece of the puzzle.
Exactly. If we could find the graviton, it would be huge. It would really confirm this whole idea of gravity being a quantum force, and that would open up a whole new chapter in physics, it would be
Like discovering a whole new continent, but for physics.
Exactly. It would change everything.
So finding this graviton, that's like the holy grail for this whole new way of thinking about gravity.
It would definitely be a game changer. And you know what? It would help us finally tackle one of the biggest mysteries in physics.
Which is?
How to make gravity and quantum mechanics play nice together.
Oh, right, because right now, those two are like speaking different languages or something.
Exactly. It's like they're from different universes, even though they're both trying to describe the same one.
Okay, that makes sense. So, like, general relativity, that's Einstein's thing, and it
Right.
works great for big stuff like planets and stars and all that.
Right. Big scales, it's perfect for that. But then you get down to like atoms and the really tiny stuff.
And that's where quantum mechanics comes in.
Exactly. And so far, nobody's been able to figure out how to make those two fit together neatly.
It's like trying to put a square peg in a round hole.
Pretty much. But if we could crack that nut, if we could figure out this whole quantum gravity thing,
What could we do? Like, what doors would that open?
oh man, that's the exciting part. We could be talking about completely revolutionizing our understanding of the universe from like the Big Bang all the way to how black holes work.
Whoa.
We might even stumble onto technologies we can't even imagine right now, like totally new ways to get energy or even like control gravity itself.
Okay, now you're just messing with me.
Who knows? The possibilities are endless. But seriously, I think what we've learned today is that gravity, it's way more than just what keeps us stuck to the planet, you know?
For sure. I mean, I thought I knew a thing or two about it, but this article, it totally blew my mind.
That's the beauty of physics, right? There's always something new to discover, even about things we thought we understood.
Absolutely. Well, I think that about wraps it up for this deep dive. Big thanks to you. This has been an amazing conversation.
Anytime. Glad we could geek out about gravity together.
And everyone listening, keep those questions coming, and we'll keep digging deeper into the mysteries of the universe. Until next time.